Okay, so let's review real fast. Partial fraction decomposition. What is it? What's it about? Why do we care? There is a algebraic theorem that says that there are two algebraic fractions that add up to this fraction right here. Okay, and because the denominator is factored, I can tell that the two factors of the fractions, the denominators of the fractions, are going to be y plus 4 and 2y minus 1. There are two fractions that when you add them together will give you the original fraction on the left here. We don't know what these numerators are. That's our mission here, that's our goal, and you'll see why that's useful for integration in a second here. But since we don't know what those are, we will put the constants a and b in the numerators there. Okay, now how are we going to go about finding a and b? Well, if I was presented with the sum of two fractions and I had that equal to this, I'd want to add these two fractions together with a common denominator. So I'm going to go ahead and do that. I know the denominator will be y plus 4 times 2y minus 1, just as it is on the left. And I'm going to go ahead and just write down what you're going to get for numerators here. You're going to get a times 2y minus 1 plus b times y plus 4. Okay, and that's equal to the original fraction on the left side here. Okay, so we have denominators equal to denominators. That means that for these two fractions to be equal, the numerators must be equal to each other. So I'm going to go ahead and drop the denominators and just look at what I have here. Y equals, and I can go ahead and multiply this out now, okay? 2ay minus a plus by plus 4b. What I want you to see here is a relationship here. As far as constants go, I have 0 constants and I have 1 y on the left side here. And I'm going to create a system of equations here based on what I have on the left versus on the right. Okay, it's a little bit different, but it makes sense, I think. So as far as constants go, 0 is got to be equal to the constants on the right-hand side of this equation, which is negative a plus 4b. And 1y has to be equal to 2ay's plus by's. Okay, and here I have just a plain old two-variable, two-equation system, which we've done many, many times. This one's not a problem. We don't need any new technique here. So I'll just go ahead and do this how we probably normally would in the past to solve for a and b. My first instinct is to eliminate the a because I have a 2a here and a negative a here. And so multiplying the first equation by 2 will do that for me. And then I can add it to the second equation to get a equation that only has a b in it. So let's see, what am I going to get here? I'm going to get 0 plus 1. I'll get 1 is equal to 0 a's, that's what I want, and I have 8 b's plus 1 b, so 9 b's. And so b is equal to 1/9, and then I can use either equation to get a. So I'll use it this one right here. So 1/9 on the right side, subtract it over here, I'll get 8/9. Divide by 2, I'll get 4/9, so a is 4/9. And so those were my mysterious coefficients, or my mysterious numerators up here. And so I can now go ahead and replace a and b with what we found them to be, 4/9 and 1/9. And we don't like compound fractions, so 4, and I'll put the 9 in the bottom here, 4/9, and then plus 1/9 for the second one, okay? And if you add these two fractions together, you're going to get this one over here. Let's double check here. So we thought 4/9 was, I'm sorry, 1/9, yeah, 4/9 is a, and 1/9 is b. So let's just double check this here, okay? Make sure we're correct. So we would get 8/9 y minus 4/9 plus 1/9 y plus 4/9, okay? And the 4/9 are going to cancel, and 1/9 and 8/9 gives me 9/9, which is 1y, which is what we had. So that's really good, okay? We've done our job here. Now, I'm going to borrow this right here and copy it and go to the next page, because here's our calculus mission here. I need to do the integral of that original fraction, and you need to decompose it into partial fractions in order to do that. So we've done that for this problem, so I don't have to go through that process again, but I want to show you here why knowing how to do partial fractions was so important, okay? And how do you know to do partial fractions? All right, first of all, if I just look at this integral, it's not going to fit into any of my basic patterns. It's not going to be a u sub, and it's not going to be integration by parts. The product is in the denominator. That's not really good for me. When I have broken it into partial fractions, and if I split this into two different integrals and take out the 4/9 here, I get 1 over y plus 4 dy, which is a very nice integral to do. It's going to be an ln, and this one would be 1/9 integral 1 over 2y minus 1 dy, and that's also a nice one. Those are both going to be ln's. This one does not need a u sub because the denominator's derivative would be just 1, so this will just be 4/9 times the natural log absolute value y plus 4. This one would require a u sub because the derivative of the bottom is 2, so we have to fudge into 2, which means balance with a half. So over here you get 1/18 times the natural log absolute value 2y minus 1 plus c. Okay, so that's the basic case. Two linear factors will come out to be two different fractions with linear denominators, and these always end up being ln's in the cases that we're going to see. Alright, so for your first problem, try 7.4 number 9, both versions. It's very similar to this one right here. Pause the video, and when you're ready, we'll resume with the next stage of the process. Okay, now, this one will be same deal, but it's going to have now more than just two factors in the denominator. It'll have 3. Okay, so let's go ahead and factor the denominator first here. Again, how do I know I'm doing partial fractions? Well, I go through my process. It's not on the list. It's not a u sub. I could factor the numerator and think of it as parts, but it's going to be messy. The denominator factors, and that's going to be kind of the key buzzword, the key clue that's going to tell me I'm going to be doing partial fractions. If I can factor the denominator into linear factors, I'm probably doing partial fractions here. Okay, so this is my fraction now, and that fraction could be rewritten as something over x plus something over x minus 1 plus something over x plus 1. That's what we're going to go do off to the side here, and then we'll return to the integration when we're finished figuring out what those constants are. Okay, so what do we have here? We're going to have some number a over x plus some number b over x minus 1 plus some number c over x plus 1. Okay, now if you'll remember, what we did on the last problem was we got a common denominator, but then all we were really worried about were the numerators being equal to each other. So I hope that if I do this it doesn't confuse you, but I'm just going to say, okay, I've got the numerator on the left here, and it's going to be equal to the numerator on the right when I'm finished. Now, how do we get that numerator on the right? This a needs to be multiplied by the two pieces of the denominator that it does not already have, so that a is going to be multiplied by the x minus 1 and the x plus 1, like this. The b is going to be multiplied by the x and the x plus 1, and the c will be multiplied by the x and the x minus 1. Okay. Now at this stage, you could do what we just did and multiply all this out, create a system of equations, and solve the system. And that's fine. That will work. This tends to be a little bit faster, and I think you'll like it. Okay, this is called the Heaviside method. It's not really important what it's called, and I don't even remember how to spell it. I don't know if it's Heaviside or not. I can't remember. But this is named after a mathematician, and this technique's kind of cool. So, Heaviside method. Okay, here's what we do. We're going to make this a little bit easier to solve for A, B, and C. And you're going to kind of laugh when we do this here. So let's do this in different colors. So blue. All right, we're going to pick a x value here. Okay, and we're going to pick an x value so that two of these guys vanish, and only one will be left. Okay, so notice that if we let x equal 1, okay, if we let x equal 1, then this term that has the a attached to it will disappear because I'll have a 0 in the second factor of this expression. Okay, so if we let x equal 1 in the entire equation here, you're going to get 1 plus 2 plus 1, that's 4. 4 is equal to 0 plus, watch me now, b times 1 times 2, okay, 2b, and then the c term also cancels out because if x is 1, then this last factor is 0. Okay, and look what happened. Everything died, and I have something very easy to solve. 2b equals 4, which means that the b is equal to 2. Okay, very nice. Now let's do the same thing. This time let's let x equal -1. And you'll be amazed how simple this is, but it works out real nice. Okay, well here we get 1 minus 2 plus 1. So that's a 0. 0 is equal to, this guy with the a's is still 0. The guy with the b's is still 0 this time. And now the guy with the c's is going to be, let's see here, c times -1 times -2. Let's double check that here. -1 minus 2 is -2 times the -1 is 2c. That becomes a 0, that becomes a 0, and this becomes a 0. And does that make sense? Actually, it does make sense, because if we go back over here and factor the numerator, x plus 1 times x plus 1, we could have removed the x plus 1 term from the numerator and the denominator. Okay, so that's why that ends up being a 0 there. Doesn't always happen that way. C equals 0. Okay, and one more time, let's do one more of these, and we'll get what the a is going to be. So if we let x equal 0, then we'll figure out what a ends up being here. Let x equal 0. Okay, the left side is 1. 1 is equal to, notice that both of these come out to be zeros, so we have -a is equal to 1, so a equals -1. Okay, the algebra is now done, and now we're ready to do the calculus. Oh wow. Okay, this won't be so bad because it's only going to be 2, it turns out. Sometimes there are 3, and we got to do this 3 times. Okay, so my original integral is now what? A is -1, correct? -1 over x. B ended up being 2, so 2 over x minus 1 dx, and those are two very nice integrals to do. So the first one's the negative natural log absolute value of x, and the second one will be 2. No u sub needed here because the derivative of x minus 1 is 1. So it's 2 times the natural log of x minus 1 plus c. Okay, very nice, very cool. Now the one that you're going to get to do will have a c that's not equal to 0, but that's no big deal because there'll just be a third natural log in this process. Give it a try with the Heaviside technique. I hope you like it because it's kind of fun. 7.4, number 17. Pause the video. Okay, third stage of the process here. All right, I'm going to put a little note up here for you. Partial fractions only works with quote-unquote proper fractions. Okay, so in other words, a fraction where the degree of the denominator is larger than the degree of the numerator. That has to be the case, or else we can't use partial fractions. It won't work out for us. So notice over here, the degree of the numerator is third degree. The degree of the denominator is second degree. We cannot do partial fractions on this guy yet, so we have to do something first, and the answer is long division. That's right. More algebra review here. And we can't even use synthetic division here. We have to do the old school long division algorithm that we all love so much. Okay, so what are we doing here? We're doing x cubed minus 4x minus 10 divided by x squared minus x minus 6. Okay, so remember how this works. X squared goes into x cubed. Well, in other words, x squared times what gives you x cubed? X is the answer. Then we multiply. x times all three of these terms here. X cubed minus x squared minus 6x. We're going to subtract this entire expression here and see what we get when we're finished here. Excuse me. X cubes cancel. There are no x squareds up here, so 0 minus a minus gives me a positive x squared. Negative 4x minus a negative 6x is a positive 2x, and then the negative 10 comes down. We see if we can do this again. X squared goes into x squared one time, so positive 1. We multiply 1 times x squared minus x minus 6. Subtract this entire expression, and here's our remainder, because now we'll be finished. X squareds cancel. 2x minus minus x is 3x. Negative 10 minus a negative 6 is a minus 4. Okay, what the heck did we just do, and what does this mean? It means my integral is equal to this. This is my quotient, x plus 1. That's the part I like. And then my remainder is what? 3x minus 4 divided by what my divisor was, x squared minus x minus 6. Okay, here's my dx. And now I'm ready to go. The first two terms are easy to do, and then the last piece is going to require partial fractions. And let's go ahead and decompose this fraction right here so that we can finish the calculus part here. 3x minus 4 over, now if we factor the denominator, we're going to get x minus 3 and x plus 2. So we know that that's going to be equal to some number over x minus 3 plus some other number, b, over x plus 2. Okay, and then using as many shortcuts as possible here, 3x minus 4 would be equal to the new numerator that I would get when I add these two fractions. What's that going to look like? A times x plus 2 plus b times x minus 3. And let's go ahead and use Heaviside here, because it's fun. Let me go back to a thinner pen, because I'm starting to get sloppy, I think. All right, here we go. Let's let x equal negative 2. The a term will cancel out. Here you're going to get negative 6 minus 4, so negative 10 is equal to negative 5b. Great. B is a nice whole number. B is 2. Okay, and let's do this again. Let's this time let x equal 3. So if the b term cancels out, now we're going to get 9 minus 4. 5 is equal to 5a. Looks like we got an example that was rigged for a success. A is 1, and now we're ready to do some integration here. Okay, so we can now replace 3x minus 4 over x squared minus x minus 6 with what we just got over there, which is, let's see here, a was 1, so 1 over x minus 3 and 2 over x plus 2. All right, dx, and now the integration is pretty simple. We get 1/2 x squared plus an x plus the natural log absolute value of x minus 3 plus 2 natural log absolute value x plus 2 plus c. You get to go ahead and try, not one from the textbook, but one I actually made up. Okay, x cubed over x squared plus 4x plus 3. Long division first, and then get into the partial fractions. Okay, this last slide here is just to show you that there are more techniques. In fact, this section 7.4 is loaded with integration techniques that we're not going to talk about, but they're still good to know. They're not on the AP test. So I'm just going to talk real quick about two little scenarios that pop up. The first one is this x squared is not a linear factor. Okay? It would be called a repeated linear factor because you could factor this as x times x. So the same factor is repeated twice. And so when you would go to do your decomposition, okay, this would be equal to a number over x, but the fraction could also have been contributed to by a number over x squared. We don't know. And since we don't know, we need to account for it here. And then a number over x plus 1. Okay, so there's a little nuance to partial fractions. It's when you have a repeated linear factor. In this case, it was x minus 0 squared is repeated, so that needs to show up in decomposition. And then this also is a little nuance here. This one has a what's called irreducible quadratic factor. This does not factor with real numbers. Okay, so you have a quadratic piece down here. So how does this get handled here? Well, I would still have, for the x plus 1, that would still be a number over x plus 1. And since x squared plus 4 is quadratic, it's possible that I would have not just a constant piece in the numerator, I might have a linear piece as well. Because remember, this works when you have proper fractions. Well, if I have a quadratic, I couldn't, in theory, have a linear factor up here. Okay, so this would be bx plus c. It could be a linear piece with a constant piece, in theory. We don't know until we try it out. Okay, so if you're curious and want to try those out, go ahead. These are not tested on the AP test, but if you go up to Calc 3 or retake Calc 2 in college, you may see these techniques used, and it's good to have seen them before.